So let's go back to how this wave-particle duality or wave nature of the electron affected our understanding for the atomic structure. The electron inside the atom is moving within boundaries. So it's actually like a wave moving within a fixed string, like a guitar string or something. It's going to propagate back and forth between the beginning and the end of the string. It's not able to propagate outside these two limits. So that will cause it to go back and forth and make what we call a standing wave. So in order for a standing wave to be sustainable, it will have to move like this, with a physical motion or a wave motion that can move any point on the string, but the beginning of the string and the end of the string, because these 2 points are actually fixed in place and cannot physically move. So any wavelengths that will allow moving the string without moving these 2 parts is going to be allowed. So any whole loop is going to be allowed. Multiples of a whole loop are going to be allowed. 2 loops, for example, as you can see in this picture right here, or even 3 loops or 4 loops. Fractions of a loop are not going to be allowed. For example, this mode right here is involving fractions of a loop that would require the beginning of the string and the end of the string to move, which is physically impossible because these 2 points are actually fixed in place. So it's impossible to move them. Any waves that would require them to move is not going to be an allowed wave. So based on this idea, we will only have a specific set of allowed wavelengths that corresponds to multiples of a loop, either 1 loop, 2 loops, 3 loops, and so on. And that means that for a standing wave on a string, only specific waves or wavelengths will be allowed that corresponds to multiples of a loop, which is called a quantum number. It's gonna be either 1 loop, 2 loops, or 3 loops, and so on. So what determines the allowed wavelengths in this case is gonna be the number n, the integer n, 1, 2, 3, and so on. That's why we call it quantum number. It's a whole thing, a whole loop, 1, 2, 3, 4 loops. And since the energy is inversely proportional to wavelengths, and the wavelengths in this case is going to be proportional to the quantum number, the number of loops, energy itself is going to be proportional to quantum numbers. So only multiples of a loop will be allowed, or wavelengths that correspond to multiples of a loop will be allowed, 1, 2, 3, 4, and so on, which means only certain values of energy that corresponds to these wavelengths will be allowed. And that's the concept of quantization. It means that only certain values of energy will be allowed. Nothing in between will be allowed, because having an energy in between these two values is going to mean that you will have to move the string in a wave motion that would require the beginning of the string or the end of the string to actually move, which is physically impossible. Okay, that's here is basically the concept of quantization of energy. Only certain values of energy are going to be allowed, or only certain modes of wavelengths are going to be allowed. So if you apply this to a circular orbit like in an atom, it's going to be the same thing, except the boundaries of the orbit in this case is going to be the radius, the distance from the nucleus, if you consider that the nucleus is here in the middle. So you will have 1 loop type of mode, like you can see in this animation right here, 2 loops type of mode, so a distance that would allow 2 loops two complete loops to exist, and so on. The electron cannot move in between these two distances because the wavelength is going to correspond to a fraction of a loop, which is physically impossible. It's not a sustainable mode to take place. That explains why only certain orbits are allowed. So based on this idea, inside the atom, Bohr's model to describe the atom says that inside the atom, only certain energy levels that correspond to certain orbits at very specific distances from the nucleus will be allowed. And these orbits or energy levels are going to be determined by an integer n, a whole number called a quantum number. In this case, it's called the principal quantum number. And you basically will determine the allowed values of energy based on the corresponding quantum number. And the magnitude of the energy in this case is going to be inversely proportional to the square of the quantum number. So the only thing that determines the magnitude of the allowed energy levels in the atom is going to be only the quantum number, nothing else. Okay, this is just a proportionality constant. So the allowed energy levels are going to be corresponding to the allowed quantum numbers. Quantum number 1 is going to give you the energy of the energy level 1, and so on. And for a hydrogen atom, that's the value of the proportionality constant for this formula, which is called Rydberg constant. Okay? And n, as we said, is the principal quantum number. So if we want to calculate the energy of the second energy level in a hydrogen atom. So the energy of any energy level is given by the formula En equals minus RH times 1 over n squared. So it's gonna equal minus, this is the value for Rydberg constant, which is 2.18 times 10 to a negative 18 joule times 1 over the quantum number of the energy level. It's 1 over 2 square. So it's gonna be minus 5.45 times 10 to negative 19 joules. Just to visualize this idea of only allowed atomic orbits or energy levels, you can think of it as layers of onion. The nucleus is in the middle, while the electrons can only exist on the boundaries of a layer inside the onion. It cannot exist within the layer itself. And based on this concept, you can clearly explain why you see a line spectrum when you excite an atom. Because what will happen is that the electron can jump from one allowed orbit to the other. So it's gonna move in jumps between the allowed energy levels only when it gains energy that equals the difference between the starting energy level and the ending energy level. Only when you shine a photon that has energy equal to the difference in energy between the starting energy level and the end energy level is when the electron can move. So you shine a photon with the enough required energy is going to push the electron to the next energy level. That will show up in the spectrum as a line absorption spectrum. It's an absorption spectrum, meaning that it will absorb the photon of light in this case in order to push the electron flow from a lower energy level closer to the nucleus to a higher energy level far from the nucleus. And if the electron is already at a higher energy level, it's going to prefer that it relaxes back to the lower energy level. And when it does so, it's going to release a photon with energy that equals exactly the difference between the two energy levels. And this process is called relaxation, and it's going to result in emission line spectrum, emitting very specific frequency that corresponds to the energy difference between the two different energy levels. Again, just to visualize how this happens, the lowest energy level, the lowest possible energy level is called the ground state. Any higher energy level is called an excited state. The electron in a normal situation is going to prefer to stay in a lower energy level. If you shine a photon, the electron is going to jump to a higher energy level if the shine photon has exactly equal energy to the difference between the two energy levels. So it's basically as if you are throwing the ball from one step to the other. It's either stable on step one or in step two. It cannot stay at any distance between the two steps. Same thing, the electron cannot stay at any distance between the two energy levels. The process when the electron moves from a lower energy ground state to a higher energy excited state is called an absorption process, because in this case the electron would need to absorb a photon in order for this transition to take place. If the electron is already in an excited state and it relaxes back to a lower energy level, a ground state, is going to be an emission process, because the electron is going to be losing the difference in energy in the form of a photon. So that's an emission of a photon. And again, that explains what we observe experimentally when we study the light matter interaction for any atomic sample. You can either see a line absorption spectrum or a line emission spectrum based on whether it's a motion of the electron from a lower energy level to a higher energy level that would require an absorption of the corresponding photon. So it's going to be absorbing specific photons with specific wavelengths from the wide spectrum of the white light. And an emission spectrum when the electron is originally at a higher energy level and it relaxes back to lower energy levels, it's going to emit photons with energies that correspond to the difference between the starting energy level and the end energy level. And you can clearly see that the frequencies of the lines absorbed or emitted are going to be the same, because basically it's the same jump either from energy level 1 to energy level 2, or the other way around from energy level 2 to energy level 1. So it's basically the same difference of energy that the electron will emit or absorb for each one of these. And that successfully explains what we observe for the emission spectrum of hydrogen. For example, we should expect 4 different possible transitions from higher energy levels to energy level 4, and transitions from higher energy levels to energy level 3, higher energy levels to energy level 2, and higher energy levels to energy level 1. Those are all possible transitions. However, they have different frequencies for the emitted photons in each time. And it happened that the Balmer's series is actually within the range of visible light. So those are the 4 visible lines that we usually see for the emission spectrum of hydrogen. And we can accurately calculate the frequencies of each one of these transitions based on the fact that in order for any of these transitions to take place, the photon that will get emitted is gonna equal the difference between the final energy level and the initial energy level. And as we know from Bohr's model, the energy of each of these energy levels is going to be given based on its quantum number. So for the final energy level, it's going to be 1 over the square of the final quantum number. And for the initial energy level, it's going to be 1 over the square of the initial quantum number. And in order to calculate the energy of the emitted photon, is going to be Rydberg constant times 1 over the square of the initial quantum number minus 1 over the square of the final quantum number. And it's gonna very accurately enable us to calculate the corresponding energies. And from these energies, we can calculate the corresponding wavelengths or frequencies according to Planck's formula, where the energy here is gonna equal h nu, so we can rearrange and solve for frequency, or is going to equal hc over lambda, so we can rearrange and solve for lambda, which is the wavelength of the emitted photon. So in this example, let's calculate the energy of the photon emitted for a transition in a hydrogen atom from the fourth energy level to the first energy level. So just to kind of try to imagine the transition, you can just draw an energy diagram. So you have energy level 4, which is a higher energy level 1, and then the electron is originally in energy level 4 and is going to be relaxing down to energy level 1. So it's actually going to emit that difference in energy in the form of a photon. So that's an emission spectrum. And you can calculate the energy of the emitted photon to equal the difference between the energies of these two energy levels. So the energy of the photon is gonna equal the difference in energy of the two levels of the electron. So it's gonna equal the energy of the final level minus the energy of the initial level. So it's gonna equal RH times 1 over the square of the quantum number for the initial energy level minus the square of the quantum number of the final energy level. So it's gonna equal 2.18 times 10 to negative 18 joule times 1 over 4 square, that's the initial energy level for this transition, minus 1 over 1 square, which is the final energy level for this transition. So it's gonna equal negative 2.04 times 10 to negative 18 joule. And the negative sign here is actually because the atom is losing energy in the form of an emitted photon. So if we want to calculate the wavelengths of that emitted photon, we'll simply use Planck's formula, which relates the energy of a photon to its wavelengths, hc over lambda. We rearrange to solve for the wavelengths. So the wavelengths of the emitted photon is going to equal hc divided by the energy that we just calculated. So it's going to equal 6.63 times 10 to negative 34 joule second times 3 times 10 to the power 8 meter per second. And then we'll divide it by the energy we just calculated in the previous slide, which is 2.04 times 10 to negative 18 joules. And when you carry out this calculation, you will find that second will cancel out with second, joule will cancel out with joule, and you will be left with a number in meters, which is the unit for wavelengths. It's going to be 9.73 times 10 to negative 8 meters. Or if you want to express it in nanometers, you will just use the conversion factor. 1 meter equals 10 to the power 9 nanometers. So that is gonna make it 97.3 nanometers, which is basically in the ultraviolet region of the spectrum.